Section 4.1, the third part of section 4.1, solutions of linear equations. We consider the nth order differential equation a(n) of x, the nth derivative of x with respect to x, plus all, y here with respect to x, all the way to a sub 0 of xy equals to 0. This is called homogeneous nth order differential equation when it's equal to 0. But if it's equal to a function g of x, something as a function in x, is called non-homogeneous or not homogeneous differential equation. So this is called homogeneous or non-homogeneous, or the second one, based on the three conditions here, that all the a(n) of x, that's the leading coefficient there, is not 0. Gx on the right side is continuous, and all the coefficients on the left side are also continuous for all x. So assume this has a unique solution and exists. So what we do, we introduce a theorem here. This theorem is called Superposition Principle, which says if we have y1, y2 all the way to yk be solutions of the homogeneous linear nth order differential equation on an interval I, that's the first equation I wrote above. Then the linear combination, it's a combination of all these solutions, c1y1x plus c2y2x all the way to ck yckx, is also going to be a solution by this theorem. All these ci's are constants. All the ci's are constants. So it's a good theorem to know. We have corollaries to the previous theorem that follows up from that theorem. The first one says a constant multiple y equals, we call it y equals c1 yx of a solution y1 of x of a homogeneous linear differential equation is also considered a solution. So what this is saying, if this is a solution, then a multiple constant of it is always automatically a solution to that differential homogeneous equation. That's the first one. The next one, it says that the homogeneous linear differential equation has always y equals 0 as a trivial solution. Y equals 0 as a trivial solution. Just keep these two things in mind. And to apply the first one, let's say, given y1 and y2 both are solutions of this differential equation, x cubed y double prime minus 2xy prime plus 4y equals 0 on the interval 0 to infinity. Then, based on the previous theorem, or the superposition principle, guarantees that c1x squared plus c2x squared ln of x, which is the linear combination of these two solutions, is also a solution for this given differential equation. Also, as another example, if y equals x squared is a solution to this differential equation as given on that interval, then automatically a multiple constant of it is a solution, is a multiple solution. Note, if we take c equals 0, then you will get the trivial solution. That's what the second part of that corollary means. Now you can test it if you like, or check it out. Find the first derivative and find the second derivative and substitute them into this equation. You should get 0 on both sides of the equation. You should get 0 on both sides. The next theorem we introduce here, those are called linearly independent solutions. If we let y1 to yn be n solutions of the homogeneous, not for the non-homogeneous, just for the homogeneous, the equation that equals to 0, linear nth order differential equation interval I, then the set of solutions is linearly independent. We say that set of solutions for that equation linearly independent on I, if and only if, which means you can go both ways. The Wronskians for this is not 0, if you remember this from the previous part of this section. The W means Wronskians for y1 all the way to yn is not 0. So that's what this is saying. Note, any linearly independent set of n solutions of the homogeneous linear nth order differential equation on I is said to be a fundamental set of solutions on I. Fundamental set. So if you come across something what talks about fundamental, that's what it is. Any linearly independent set is called a fundamental set. And I will add one more note about this theorem. It's kind of like the opposite or reverse of this theorem. What happens if the Wronskians is 0, what we get. But first, let's look at this one. Another theorem talks about constants and their existence. If y1 to yn, all of them are solutions of the homogeneous differential equation, then any solution, capital Y of x, can be written as a linear combination of the constants, provided that all these solutions exist. Now, definition, if y1 all the way to yn are solutions to the given homogeneous differential equation, then y, the one that we wrote earlier, c1 y1 all the way to cn yn, that's the linear combinations, is called the general solution of the differential equation. Some people use y sub g for what general solution to represent the general solution of the differential equation. If we look at this example here, y double prime minus 4y equals 0 has two solutions, and later on we will learn where these came from in the subsequent sections. Then we can say that if we find the Wronskians for this, for the e to the 2x and e to a negative 2x, by differentiating once and finding the determinant this way, minus this times this, you get negative 4, which is not 0 for all x. This means for all x. Then the linear combination is the general solution for that differential equation for the given y double prime minus 4y equals 0 differential equation. So if the Wronskians is not 0, then the linear combination is a solution. And this follows from this theorem right here. So what we proved, that's what if and only if means. If and only if means if the Wronskians is not 0, then the set of solutions is a linearly independent set of solutions, and vice versa. If the set of solutions is linearly independent on I, then the Wronskians must not equal to 0. That's what this example is. Now, how about non-homogeneous equations? How do we work with this one? To work with non-homogeneous equations, we start by introducing what we call y sub p. This is a particular solution. Particular solution to the differential equation. Example, let's take an example on this to start with. Y sub p, which is x cubed minus x, is a particular solution. To the differential equation x squared y double prime plus 2xy prime minus 8y equals 4x cubed plus 6x. And how do we verify that? To verify this, we find y prime for the y sub p, which is 3x squared minus 1, and y double prime 6x. Substitute. What do we get? X squared times 6x plus 2x, 3x squared minus 1 minus 8y. And let's see what we get. I substitute only in the left hand side. Distribute this out. 6x cubed minus 2x minus 8y. But the y means y of p is x cubed minus x minus 8x cubed plus 8x. What do we get? 6 plus 6, 12, minus 8, 4. And this plus this is 6x. And that gives, it matches this one. So usually that's the particular solution. We call particular, usually it's the solution for the one on the left side. And then we extend it to more solution, general solution for the entire equation. So we can say for any non-homogeneous homogeneous differential equation, we can say y equals the one we start with, y1, c1 y1 of x plus c2, the linear combination one, all the way to ck y sub k of x plus y sub p of x. This we can replace this with y sub c. Instead of writing it every time, we can just replace it with y sub c. So y sub c plus y sub p of x. This is the general solution for the homogeneous, non-homogeneous nth order differential equations. So later on we will learn how to find the underlined one and the particular and combine them together. Here we're just trying to verify that this is a particular solution and the difference between homogeneous and non-homogeneous differential equations. Now, to set on the side more stuff, slightly different, let's look at, sometimes you can be asked to find interval or intervals for which the differential equation x dy dx plus 3y equals 4x squared has unique solutions. With y of 1 equals 2. How do we do this? Well, we first take the equation, divide everything by x, rewrite it, dy dx plus 3 over x y equals 4x. So here what we have this is p of x, we call it 3 over x. We have either you can call q of x or f of x, and it's 4x. So notice p of x is continuous everywhere except at 0. So over the interval negative infinity to 0, union 0 to infinity. And f of x is continuous everywhere, negative infinity to infinity. Therefore, these two functions are continuous over negative infinity to 0, union 0 to infinity. So everywhere except 0. Note, it's given that y of 1 is 2. So we are working only over this interval here. So this tells us the interval that they're asking for is simply 0 to infinity. That's the interval for this given differential equation to have a unique solution. So always rewrite it in this form. So rewrite any given differential equation in the form to find that interval, dy dx plus p of x, as you can see here, y equals f of x or q of x. Find the domain for this, and then intersect them. So you find domain of p of x, domain of f of x, intersect them, and try to watch for the condition. The given condition. From there you can get the interval where the given differential equation has a unique solution.